Okay. Grabando.
Okay. So hello everyone, and thanks for attending this new seminar from the IAA. Today is our pleasure to have with us Dr. Ignacio Nigueruela, who will be talking about young massive clusters Gaia era. Okay. Okay. So hello everyone. Sorry about that. So Ignacio Nigueruela is a full professor in astronomy and astrophysics in the Universidad de Alicante since 2017. He started his career at the University of Alicante in 2002 as a Ramon y Cajal Fellow, and then from 2008 as a full professor. He got a license in physics by the University of Zaragoza in 1993, and he made a PhD about the properties of X-ray binaries in the University of Southampton. Then he has been working in different institutions in the United Kingdom, Italy, France, etc. In particular, he has been working for the Italian Space Agency. He has been teaching in different universities, and he's currently teaching both physics and astrophysics in the degrees of physics and mathematics in Alicante. His research is focused in the properties of an evolution of the massive stars, much bigger than the Sun. And he has been PI of 7 national projects on the subject, and he has also supervised or co-supervised 6 PhDs and different postdoctoral researchers on the subject. He has also made different research stays in the United Kingdom, in the United States, Chile, and South Africa. So, Ignacio, the floor is to you.
Yeah. Thank you very much for the introduction, and it's really a pleasure to be here and be able to present some of the work we've been doing over the past few years with Gaia in this nice auditorium at the IAA. Okay, my talk is called Young Massive Clusters in the Gaia Era, and it's not moving.
Yes, click on the
Oh, okay. So it is being recorded. Okay. And just a brief outline of what I'm going to say. I'm going to start with some context to make clear what I mean, and going to show changes introduced by Gaia, and I'm going to talk about the capabilities and limitations of working with Gaia on big open clusters. Essentially, what we can find and where we have to stop, mostly because of extinction, which is the big problem when looking inside the galaxy. And if I have time at the end, I will mention a few things, but maybe I don't. Okay, so context. The context is, say, that broad astrophysics in this decade is generated a new interest in massive stars because of the detection of gravitational waves. These gravitational waves are created by the merging of compact objects, and these compact objects, be them neutron stars or black holes, are descendants of massive stars. And as you see, since the first detection, that was already quite a few years ago, we've been finding lots of mergers from black holes, which are quite massive compared with what we see in the Milky Way. At the same time, there's a lot of interest in supernovae. There are big surveys conducted to identifying new supernovae. The number of supernovae known has increased by several orders of magnitude in a few years. And this is leading to new classifications and big statistics on the properties, and also to the search for their progenitors. The progenitors of supernovae, again, are massive stars, and there's a big interest in trying to understand which sort of supernovae are caused by which sort of progenitor. And again, a lot of work is being dedicated to finding these progenitors in distant galaxies, trying to understand whether they are red supergiants, blue supergiants, or some other sort of terminal massive star. All these can be explained in terms of this nice picture that we have here, in which essentially we start with a couple of massive stars in a binary. The initial parameters are varied, and you have many options and many possibilities to choose from, but you let them evolve, and they go through a number of phases in which mass is transferred from one to the other and backwards, and they form also of exotic systems, such as X-ray binaries here, common envelopes, and may produce perhaps theoretical objects. These are theoretical, no one has seen one of those. And then different sorts of binaries with compact companions, such as neutron stars, black holes, that if they survive the successive supernova explosions, may lead to these sort of progenitors of the gravitational wave systems that we see. And of course, this is very nice and very neat, but it's not quite real. There are a lot of difficulties in modeling these things. I'm not going to go into any details, because the one good thing about modelers is that you point out a problem and they tweak some parameter and they solve it. And of course, these problems exist. Maybe they can be tweaked away, but others will come up. Essentially, the problem is that there's a lot of physics hidden behind this simple picture, and we have a lot of uncertainties that come mainly from three different big groups. Uncertainties in how, let's say, single massive stars evolve. There are many things that go into the physics of a single star, even though we now think that most, if not all, massive stars are in binaries. Not all of them evolve via mass transfer. If they evolve via mass transfer, there's a lot of uncertainties as to how mass is transferred, how much angular momentum it takes with it, how much is lost from the system, and so on. What happens with the stars that receive a lot of mass? Do they become main sequence stars again with a higher mass? Do they have weird structures? And finally, there's a lot of uncertainty on the initial parameters that we must put into the models with these initial mass ratios, initial orbital distributions, initial eccentricity distributions. So if we want to learn about those things, we have to look at massive stars in the universe, and there are many problems involved. There's also the role of metallicity. Here you have an example from the work we did a few years back, in which you can see that what we call a red supergiant in the SMC is completely different from what we call a red supergiant in the LMC or the Milky Way, or this other one in which you see that most of the most massive stars in the SMC seem to be behaving in ways that are not predicted by the models. But if we don't understand massive star evolution close to us, going to distant galaxies to try and to understand the effect of metallicity is going to be even harder. Fortunately, we have the SMC and the LMC that which are close nearby, and so you can do lots of things with them. But we want to look at things that are even closer to us to understand much better what is going on. So first thing I want to do is to define what is a young massive cluster. And of course, the idea of massive depends on the context. Someone who does a star formation in the solar neighborhood thinks that a cluster is something with 50 stars. Someone who does globular clusters thinks that a massive cluster has to have millions of stars. So given the conditions in the Milky Way, it was generally agreed that we will call a massive cluster something that has an initial mass of about 10,000 solar masses, which is a completely arbitrary number, but it means something. And basically what it means is that this cluster is going to have enough stars of some given kind that you can perform statistics on them and have an experiment with just that cluster. And the experiments you can do are very different depending on the age of the cluster. You can do things like evolution of rotational velocities or distribution of stellar masses. What is the IMF in a very dense environment? Or study how stars are ejected from the clusters. There's many things you can do with a single cluster if it is big enough and you have enough stars to do statistics. Everyone's idea of a massive cluster is something like this. This is NGC 1755 in the LMC. Is a very big cluster with lots of red supergiants, which appear here sort of golden, and lots of stars. And you see is a ball, and it's big. And this type of objects are generally called young globular in the Magellan Clouds. And you can see a paper from about 25 years ago in which they say that these clusters are not as big as those that you find in the starburst galaxies, which generally tend to have perhaps 1 million solar masses, but they are big enough to serve as proxies, and also they are much bigger than anything that we see in the Milky Way. This is not entirely true nowadays. We have found many massive clusters in the Milky Way over the last 25 years. And also, we believe that some of the masses of these clusters were a bit overestimated in the past. Of course, these two here are probably really massive, with masses above 100,000 solar masses, NGC 1850, which is about 100 million years old, and the thing in the middle of 30 Dorados, which is very, very young. But the cluster like the one I just shown, 1755, probably has between 20 and 30,000 solar masses. So it's a big cluster, but certainly not a globular cluster. And in the galaxy, we've known for some time that there are big things as well. This is M11 from the Messier catalog. And already in the 70s, people were estimating rather high masses for this cluster. And of course, they didn't understand the shape of the IMF down to subsolar. And nowadays, when you do calculations, basically you find that this cluster has a percentage mass of about 10 to the 4 solar masses, meaning that it was more massive in the past. How much depends on many assumptions that you can do about evolution of the massive stars that were there and have all already died, and the dynamical evolution of the cluster and how many stars have been ejected from it. But we have things which are relatively big as well in the Milky Way. Why do we think that these things are interesting? As I said, they can be used to conduct experiments, but also they are proxies of the starburst conditions. We are never going to go to a place where you are forming a 1 million solar mass cluster. We are never going to go to the era in which the globular clusters were formed. So we have to go to something that is similar, where you can find, you can study the IMF under extreme conditions, and you can do other things connected to lower mass stars, like seeing if their protoplanetary disks can survive in the harsh UV environment produced by the massive stars. And if the cluster is young enough, you can find there the most massive stars, see how massive they get to be, see which ones are their extreme properties. And if the cluster is moderately young, you can see the evolution of high mass stars in context. So many things you can see in a big cluster. Just as a comparison, this is a normal cluster, what we call a normal cluster, one of the better, probably the best studied cluster in the most well-studied cluster in the solar neighborhood, the Orion Nebula cluster. There's been different estimates of its mass. The cluster contains 4 obvious stars in the middle, the trapezium, and there are 3 in the intermediate neighborhood, but these are all multiple systems. So the number of obvious stars is higher than 7. We know this because they are very close and we can see there are multiple. The mass of the cluster was estimated at about 1,800 solar masses. There's some discussion about this number. Some people argue that there's a foreground population that has to be separated, but somewhere between 1 and 2,000 solar masses, you have a few obvious stars. And this is something that you expect because in general, you can find a correlation between the total mass of the cluster and the mass of the most massive star that you find within the cluster. There's a lot of discussion that I'm not going to get into about whether this is simply a stochastical sampling from an IMF that is statistical, or if there's something behind this. Not going to go into this because it will be a seminar of its own, but in general, the correlation exists and is good, and so a few O-type stars means 1 to 2,000 solar masses, and that's your lower limit to have massive stars. And so you see that 10,000 is about 10 times bigger, which is bigger. So Gaia. I don't think I need to introduce Gaia to anyone. It's a wonderful machine that's been flying for almost 10 years now and collecting data. And behind it, there's a huge number of scientists in GPAC, which are processing really unbelievable amounts of data and producing very, very nice astrometric solutions for all of us to enjoy. One thing to take into account is that the DR2 astrometric solution that was published in 2018 was still subject to many systematic effects and uncertainties. Most of the work that we've been doing until last year, more or less, was based on DR2, and DR2 had its limitations. Parallaxes were good for individual stars out to about 1 kiloparsec. Of course, for a cluster, you can mix together a lot of stars, you get a much better parallax for the cluster. But in many respects, DR2 was good for skywide populations, internal comparisons, not for giving good distances to things that were far away. Thing has completely changed with DR3. Now the astrometric solution is much better. The systematic effects are mostly understood and residuals are small. Parallaxes are good for individual stars, probably out to 3 kiloparsecs. Values for clusters are very valuable, out to 5 kiloparsecs, probably, unless you have a lot of extinction that renders the stars very faint. And of course, DR3 has exquisite proper motions that allow you to separate members from non-members of a cluster very easily, to define what is the cluster, what is not the cluster, and to look for dynamical effects within the clusters. So this has really led to a revolution in cluster science that is happening at the moment, especially studies of nearby clusters have exploded. People can see the internal dynamics, people can see the tidal tails of the clusters, they can see clusters merging, clusters moving, they can see a lot of things nearby. But even if you go further away, you can see a lot of very interesting things. This is the latest catalog of clusters that was being published this year. And you can see here, this is a selection of clusters that, according to their automated algorithm, which works sort of okay, are younger than 100 million years. And you can see how now we are able to see clearly by eye the spiral arms of the Milky Way, which is something that had never happened before. You can see them. Another thing is that they don't correspond to the spirals that the models show, but you can perfectly see the large, for example, here, the Perseus arm. You can perfectly see it defined here. You can see the local arm extending here, Sagittarius arm extending here. And this is really telling you that the distances now are very, very good. And there are many surprises coming out about clusters that are not where we believe they were. Some are near, much more near than we thought, others are further away. And for example, just to give you an example of something we are working on, this cluster in DC663 is a Perseus arm cluster. It has been studied, not much, but there have been quite a few studies because it has a very high content of emission line stars, and it's the core of the Cas-OV8 association. And it was supposed to be one more cluster. Now Gaia has moved it a wee bit further away to close to 3 kiloparsecs. And when you look at these CMD here, from simply with Gaia data, you can count more than 400 B-type stars in the image. And of course, if you have more than 400 B-type stars, you have a very big cluster. This cluster has certainly more than 5,000 solar masses and probably had an initial mass that was rather higher than that. So things that you thought were normal are coming close to the definition of massive cluster. The opposite is also happening. But there's a big problem, and Gaia's big enemy is extinction. If you look back at this image again, I've shown you the different structures, and there's something which is quite evident. The sun is here, these blob are all the young clusters that are around us, small clusters, most of them. And the galactic center is here. So if you look at outside, you see things at 3 kiloparsecs, at 5 kiloparsecs, at 7 kiloparsecs. But if you look towards the inside, you see this thing, which is what we usually call the Sagittarius arm, and you see this thing, which is what we call the Scutum arm. And here there's an extinction wall caused by lots and lots of molecular clouds. And you can see this very well traced arc. There's nothing beyond that. But before anyone asks, they are not seeing clusters close to the galactic center. This diagram is in 2 dimensions, but there's a 3rd dimension. And actually, these things here are globular clusters, which are outside the plane. And the algorithm, for some reason, is taking 4 young clusters. All these things here and all these things here, and probably these ones here as well. So beyond this 3.5 kiloparsec mark, Gaia doesn't see clusters. And this is because of extinction. Stars are faint and their parameters are bad. And therefore, if you use an algorithm to look for concentrations of stars in the space of our astrometric parameters, it doesn't find anything obvious. And we're going to see a better example later. But even at close distances, extinction is a problem. And artificial intelligence algorithms cannot deal with extinction well at this moment. And here you have an example. This is an open cluster. It's not a it's a relatively massive one of about 2,000 solar masses or so. It's been very well studied because it contains CFIT, which is one of the main calibrators of the Leavitt law. And there was a lot in the literature about this cluster. So when you look at these algorithms that are using artificial intelligence to give parameters of clusters, you clearly see that these what they are getting is not what is in the literature. And so you plot the solutions given by this algorithm based on DR2 and this other based on DR2 as well. And this is their members, and these are the solutions they give. And of course, you can see that they are very wrong. And the reason is that they cannot deal with differential extinction caused by absorption along the line of sight. And somehow they're assuming that these few objects, which have lower reddening than the rest, are giving you the position of the cluster. And then it shows the dangers of giving the algorithm too much to choose from. Here, for example, this in the Diaz paper, it has chosen to fit an isochrone with 3 times solar metallicity, which is probably nonsensical in this context. And so you see these things sometimes get it right, but few times get it wrong. This is my take by hand. In fact, we had studied this cluster a couple of years ago, so I just put in the parameters we got, and you see there is a much better fit, even though I don't like this fit, because you see that, for example, this is the C fit, and some of the supergiants are below the loop, below the position where they should be, and there are a lot of B-type stars which are above the end of the hydrogen core sequence. So this is not quite right, and I think this is simply because of extinction, because the very broad bands that Gaia has are affected by what is called colotherms, and the blue stars and the red stars respond differently to these things. And so at high extinction, the algorithms are having problems to understand this. This later one obtains the right extinction, but it gets a completely wrong age that would put the loop up here. I don't know why. So we studied how these isochrones respond to extinction in a recent paper, and you can see essentially the Gaia isochrones have 3 parts. This part corresponds to the loops, and you succeed only for ages older than about 12 million years. Then you have an almost vertical sequence. There's a very small slope, and this corresponds to the B types, and down to this is more or less an A0 star. And then the slope changes, and you have the rest of the sequence. And you can see this is the same isochrone at different reddenings, and you can see how this part converges, because the extinction moves the isochrones along exactly the same direction in which the sequence goes. So if you haven't got any young stars, and you haven't got, sorry, any early type stars, and you haven't got any evolved stars, you cannot give an age to a cluster using Gaia data. If you have young star, early type stars, you can say that it is a young cluster. For example, this is a young cluster with almost no differential extinction, low reddening, and almost the same for all of them. And you can see that it has this almost vertical sequence for 5 magnitudes, and then the slope changes, and you can fit the isochrone very well. And here the reddening is very, very homogeneous. The few objects which are here, all of them are either B stars or binaries. If you have differential reddening, in a case like this, it becomes much more blurry. I mean, this is a very nearby cluster at only 1 kiloparsec. And even so, the differential reddening doesn't allow you to fix the isochrone very well. But anyway, you can see the change in slope that is giving you an anchor point to place your isochrone. So if you find a vertical sequence, even if you think that you cannot do anything with this cluster, it's a young cluster. And you can go and then you take a spectra of these things, and they come out being supergiants and O-type stars and the like. Because you know that there's a very long vertical sequence. That means that you have early type stars, and you have them going up to early types. So just to give you an example of what Gaia can do. This is a paper we published 2 years ago. This is a region of the galactic plane where you can see there's a lot of clouds and a lot of stars, and there's no obvious cluster at all here. But I was studying something that was behind in the infrared, and I noticed that there were a few B-type stars here, and we took a few spectra, and we thought, well, a cluster like the Pleiades at maybe 2 kiloparsecs, not very interesting. But anyway, when Gaia came along, I had a look at these fields to see if this cluster was really there, and I found this. You place here, this is what people call the vector point diagram, proper motions in both directions, and you see here the field, which is distributed all over the place, and you see here a big blob of the stars with their own proper motions. And this is very clearly a cluster. And of course, this is a good case because the blob is separated from the densest part of the field. This doesn't always happen. So you take things that are here, project them on the real space, and you see that they are extremely concentrated. But you see that they are covering a huge area, 1 degree in the sky. So this is a very big cluster, in fact. We had also observed 4 B-type stars, but when you plot the chart diagram, remember anything above this is a B star. You have more than 150, and you have a lot of things here which have the same radial velocities. We took the spectra of all of them, and they are all, let's say, bright giants, because these are stars of 6 or 7 solar masses. So you have something in the sky, and if you identify the stars and take away the effect of reddening, you can with a very big cluster. And this is something that Gaia can do just by moving to the space of proper motions and then coming back from it. And this is really nice. So why can't you see anything here? Because this is a very dense region towards the inner galaxy. If you look at the bigger field, our object is around here. This big thing here is M11, and this is called the scutum star cloud. You can see the densities here are absolutely huge. And just to give you an idea, these three clusters and this one up here were known before Gaia. So with Gaia DR2, the number of clusters known was this. Then the people from the University of Barcelona carried out their survey, automated survey using this software, and they found these green ones. And then with this more sophisticated software, this recent catalog has found all these clusters. There are many cases in which there are two, but this simply means that they have redefined the center of the cluster. It doesn't mean that it's a new cluster. But you see how many new clusters have appeared. But what's striking is that precisely where you have more stars, there are no clusters. And this is not because there are no clusters. This is because Gaia cannot find them, because there are too many stars. There are too many stars, and you see here the second problem with Gaia, which is crowding. So there are too many stars here. Parameters are not good. Gaia selects only the brightest stars, and so you cannot find any clusters in this region. Well, look at the density around it. This is the galactic plane. Of course, there should be a lot of clusters here, but Gaia cannot see them. This is just to show you that work on DR2 done by hand, work on DR3 done with sophisticated algorithms give you pretty much the same. They go 2 magnitudes deeper, but okay, I'm happy with this. So, want to talk about massive clusters, and this means taking Gaia to the limit. Of course, the place where we want to go is the most massive young cluster known in the Milky Way, Vestron 1. Vestron 1, about almost 20 years ago, we found about 150 wolf massive stars, and this wave, hand waving will give you about a mass of about 100,000 solar masses. If you do things well, star counts in the infrared imply about perhaps 50,000 solar masses, depending on models and things. So this is a very big cluster with lots of interesting massive stars. As I say, before Gaia, there were many uncertainties about its age and distance. This is work done with the infrared data, giving a very young age and a short distance. This is work we did with the supergiants, giving an older age and a higher distance, and the assumption of a standard extinction, which is probably wrong. But we couldn't really work out what extinction was. The good thing about having such a big cluster is that you have lots of interesting things, and among them you have binaries. And binaries, you can solve them dynamically, and then you get masses. And so here you have lots of things that indicate you that we're looking at masses higher than 30 solar masses and probably 40. And that gives you a limit on the age, probably. And it gives you an idea of where the cluster should be. So it was a bit surprising that in 2020, this paper came along saying that they have found that the cluster was at 2.5 kiloparsecs, because it's too close. It's too close for anything. You cannot have 12 magnitudes of extinction at 2.5 kiloparsecs. It's too close. But they've done a very neat Bayesian analysis on Gaia DR2 data. And they came to that conclusion, and there were a lot of clever people here. So we made this experiment with the data by looking at, this is a normal cluster, which is the red points, and you see the distribution of errors with the magnitude for Gaia, and you see that for bright stars, it's pretty constant, and then there's a jump here around 13, and this from here, it depends on the magnitude of the star. But when you go to Vestron 1, which is a very small concentrated cluster, you start to see that the errors are distributed all over the place. So to confirm this, we went to M11, which is an even more crowded cluster. And here you could see that the errors arrayed into different families, and it was a mess. And you're seeing here the effect of crowding in the cluster. That is somehow making the algorithm that gives you the astrometric solution go mad. But this shouldn't be present in Gaia DR3. But again, the same people come back and say, yeah, in DR3 it's 2.8 kiloparsecs. And we thought, this still cannot be. So what's going wrong? I contacted your own Emilio Alfaro, who is an expert on these things, and we ran all his arsenal of programs on the cluster. And basically, you tell the Bayesian algorithm, find me the cluster here. And he did, separates cluster from background, shows you that the cluster is where it should be. But when you look at the CMD, which is what these people didn't do, you find that the cluster is all over the place. There are blue points everywhere, and there are field stars everywhere. And you know, this cannot be, this is not a cluster.
What's the cluster here? Green or blue?
The blue. Look, you can see that there are many more reddened stars in the cluster, and this makes sense because it's a very reddened cluster with about 10 to 12 magnitudes of extinction, but you can see that there are blue stars everywhere. And so, what is the algorithm doing wrong? But if you think about it, the algorithm is doing nothing wrong. The algorithm is doing exactly what you're asking it to do. The algorithm is not a magic box that you send and say, find me a cluster. The algorithm is told to find a population that is kinematically distinct from the background or foreground, and it is spatially concentrated. So if you think where this cluster is, and think about what you just saw, you're looking from here, Sagittarius arm, Scutum arm, and the cluster which is behind. So you go through a lot of foreground, which is this arm, and you come to the next arm, and then you have an extinction wall, and the stars in the cluster, even though they are intrinsically extremely bright, are very faint in the optical, and so their proper motions have very big errors. So if you send an algorithm, it's not going to think that there's something there because these are just a collection of faint stars with very big errors. But you've asked it to find something that is coherent. So when you're looking so far away, basically galactic rotation is going to dominate your proper motions. And so it finds something that is coherent. The Scutum arm that is moving coherently with respect to you. And that's what it's showing, essentially. So what we did is help Gaia a bit and say, okay, we know that the cluster is here. These are the objects with the spectra for which we are pretty sure they are supergiants at the distance of the cluster. So let's put a line here and see where the stars are distributed. And then if you look at this, the very high extinction stars are concentrated where the cluster is. And there are few around, but the density goes down very quickly. And that's telling you that the cluster is there. So we applied a number of statistical algorithms just to be sure that this was correct. We weren't just imposing the solution. The very high reddening stars were much more concentrated than anything else. In fact, there was a small concentration at low reddening. When you plot the two of them, you see that they are separate in the vector point diagram and in real life. But if you look at the second population, and here they are normalized because there are many more blue stars, you see that this is what the algorithm is detecting. And so you have to, when you go beyond the extinction wall, you have to help the algorithm. So if you just take the stars that correspond to the what we think is a cluster, you find this astrometric properties, and you see that the cluster is extremely well defined in the proper motions and in terms of parallax, and we have a distance for the cluster, which is not 2.6 kiloparsecs. There's a caveat here, which is that we are applying the 0-point offset that Gaia is known to have, and this is dependent on the stellar properties. And you can see here that while the bulk of the population is consistent with the minus 0.03 standard correction, the stars in the cluster, which are very relevant, have much higher corrections. And in fact, it depends on the stellar properties. So you have different corrections for different stars. And there's a hint in the data, because the numbers are small, that things are not quite consistent. So it may be that the 0-point correction is not completely accurate. And here, an error of just 2 micro arc seconds will take the cluster from 4.2 to almost 5 kiloparsecs. So it's significant. The other issue is completeness. If you have here, you have in blue bright stars, in red faint stars, and you can see that there are no red stars in the central part of the cluster. And of course, this doesn't make any sense from a physical point of view. It's just telling you that Gaia is not picking up faint stars in the central part of the cluster. So these are the two problems for Gaia: extinction and cloudiness. And unfortunately, this is what characterizes massive open clusters. If you look at the distribution of young massive clusters in the Milky Way, okay, these ones here, you can see with Gaia, everything that is in this sort of direction, you cannot, or almost cannot see with Gaia. Of course, you cannot see the galactic center, because there you can only see the infrared. You cannot see here, where there are 20 magnitudes of extinction, and you have trouble accessing these things which are beyond the extinction wall. And just to give you an example, this is one of those clusters, which is at a distance of about 7 kiloparsecs. We studied it a few years ago. You can get photometry and spectra of things. There's a collection of red supergiants here. It's a very interesting, there's a very bright CFIT here in the cluster, which is also important for the calibration of the Leavitt law. But if you look in Gaia, you can only pick up a few members. And if you take the average of the parallax, is 0.07 plus minus 0.06, which is not very significant. But the big question here is that the correction for the 0 point is bigger than the measurement itself. And there you are getting to dangerous place, because you are not very sure of how well this is going to work. So for these clusters, we are still limited. Since I've been talking for too much, maybe I should skip this part, which is just, I will show you just a couple of things. Coming back to this guy that I mentioned before, is the core of the Castle V8 association. And we thought it was a very big cluster, but there are other clusters with similar proper motions and properties which are nearby. And you can see here that if you have the members determined by the algorithm, they sort of mix and get very close to each other. And in fact, the proper motions and parallax of this cluster and the proper motions and parallax of this cluster are almost the same, because they are part of an association. So it's difficult to say where the cluster finishes and where the association starts. And of course, things that are here and they are extended over the field have exactly the same proper motions as the cluster. So these are not objects ejected from the cluster, because objects that are ejected have different proper motions. So in the association, you have these things. You have things that have been ejected from the cluster, and you probably have things that have slightly different proper motions, because the formation of an OB association is determined by turbulence in the giant molecular cloud. So you're going to have small differences in velocities. So this is something I think that can give a lot of hints about star formation, and people who work on that should look at these distribution things around clusters. Sometimes the shapes you get for clusters are very weird. I mean, these are the members determined by the algorithm, for another Perseus-Arm cluster, which is about 3,000 to 4,000 solar masses. And when you see this is very strange distribution. And of course, these things cannot be gravitational bound. This is it's a bit, let's say, it's cheating the viewer a bit, because more than 80% of the stars that belong to the cluster are here in what people will call a cluster. But there's all these distribution of things around. That's very big distances. You see here, we're talking of almost 1 degree at the distance of the Perseus arm. So it's very far away, and they're all over the place, and it's difficult to understand how you get to have the distribution of objects unless velocities in the cloud are not that different from one spot to the other. So there are many things hidden here that you can find, and also you can look at the spiral structure with the clusters, and note that the Perseus arm in the models goes in this direction, but what we see goes in this direction, which is weird as well. And you have a number of objects out here which are very interesting, and we are currently looking at these things to try to see what's out there in the outer galaxy. There are not very big clusters, but there are many clusters with obvious stars that probably are going to give us information about star formation at very low densities, exactly the opposite of the massive clusters. And probably we're going to find metallicities that are quite low. And I had a couple more overheads, but I'm going to skip them and come back to my summary, which is basically Gaia is a wonderful machine to study clusters, and particular massive clusters, but it has two big limitations, which are extinction and crowding. And these, unfortunately, are the defining characteristics of many of the most massive clusters, many of the most interesting clusters in the galaxy. So it's a bit of a problem for us, but there are many things that we can do. We're going to have a DR4 that will have much better astrometry, so we'll be able to do things. And we are probably waiting for an infrared Gaia that will come, if everything goes according to plan, around 2045, which is very far in the future. But it will certainly give us many more clusters. In fact, I'm convinced that there are dozens of massive clusters hidden there. We've seen how difficult it is to re-find the ones we know are there. Just simply finding again, knowing that they are there, is very difficult. I'm sure there are many there. And I'm sure that by simply exploiting the data we have, there are many more advances that we will be able to do while we wait. Thank you very much.
Thank you, Ignacio, for this very nice talk. So now it's time for questions. For people here, please speak loudly so that people in Zoom can hear you. And people in Zoom, please raise your hand and we'll give you the floor after the questions in the room. So, questions? Okay. Okay. Okay, go right now.
So when you find the cluster through the sputum arm, do you also find spurious clusters? We have made this experience, or we believe that this is a problem in the galactic center. For example, you have a streaming motion and you have a dark cloud here and a dark cloud there, and then you have a concentrated group of stars moving in the same direction. Do you have any advice to deal with that?
Yes.
Patchy extinction.
Patchy extinction is going to give you, let's say, fake clusters. In fact, there are quite a few, not many, but a few in the catalog that I just showed. I found a few that are, you look at the CMD, they're obviously not clusters. And even so, they have gone through the algorithm. But I mean, there may be a dozen among 4,000, so it's not too bad. It's really difficult to know what to do, because that's exactly what I said. The algorithm, that's what you tell it to do, and it's looking for something that is coherent in spatial distribution and proper motion distribution. And if you look at a very distant arm, it's probably going to find that. Of course, you could try modifying the algorithm to tell it to look for 2 things or 3 things. I don't know how difficult that's going to be.
That's what.
How do you decide that it's a fair cluster? Because the algorithm look in the proper motion and position space, right?
Yeah.
And then I guess you look for the edges or in the.
Yeah, basically the CMD is like a field population and not like a cluster.
So there is no way for you to decide if a cluster is a fake cluster, just looking at the proper motion.
No, just in the astrometric space. No, if the algorithms pick it, it's because for them it is a cluster. It is a cluster, but that's why I showed this before.
Yes.
What is it? This is a field population with several branches and things mixed all over the place. And the blue ones are a field population as well. So if you find something like that, it's obviously not a cluster. Of course, as you move further away into high extinctions, you start losing a lot of stars from down here. And if you see this cut here, then you have a problem, because it's much more difficult to know what is a field population and what isn't. But
I have another one. Can you go forward into the slide that you said that there is a statistical proof? This one. Can you explain these ones again?
These are different measures of grouping in the space. So what this is showing you is that stars, to which degree stars of a given color are concentrated in the space or in the space of parameters.
Okay, this is the 2 space of parameters, right?
Yeah.
Well, thank you very much for the nice talk. I was about to ask for a Gaia, but you already answered. Is that 2024, 2025, like 2045, sorry, a like optimistic approach, or can be delivered earlier, or will be delivered?
No. They don't want it earlier because they want to have a 20-year baseline between the observations. So they've just started to move the consortium. I don't know if you've received a message from Lund in which they're asking for people to join the consortium, but they want it for 2045, which is I don't know, most of us will be retired by then, but yeah.
What they're going to follow up on that is that in the meantime, since we're here, can the James Webb help us on all this business, or it's not really the same?
I guess for the very galactic center, what Rainer is interested in, James Webb can do a very, very nice work. But of course, the field of view is very small. You cannot really do this for many clusters.
You have to convince the people of the Roman Space Telescope. The Roman has a huge field of view.
Yeah.
I mean, if I might have like one more scientific question, it was curiosity. I know nothing about these fields, so maybe there are many questions, but can this zero point that you're explaining this correction bring the Western one cluster closer, or can only bring it farther? Because it's quite a different, right? From 4.8 to 4.5.
Yeah, I think. I mean, as I said, it maybe it's possibly correct 4.2. There may be a uncertainty of about 0.02, which I think is of 2 microarc seconds, which may move it a bit closer or much further away. Well, that's the problem. But you have when the measured parallax is very small, and also you have a number of biases on how to interpret how to interpret parallax that tend to move it further away.
Well, thank you very much for the nice talk. I'm your interesting. So I have 3 questions, but maybe are more that for you to know your opinion about that. In particular, you have shown that some sample cluster with they were not that concentrated, that they have these extensions. So what the origin of this? This is maybe related to transformation, something that you mentioned that. So this is a sort of tidal structure, or is it from nature? So it was created this way, or?
It's difficult to say. I mean, tidal structures. I mean, these algorithms are simple, so they look for things that have pretty much the same proper motions. There are other more complex algorithms that try to reconstruct the structure of tidal tails. And they have used that on quite a few clusters, but not massive ones, nearby clusters, where you can sort of work out very well the movement of the cluster. And they are reconstructing tidal tails at very large distances. But of course, at very large distances, you have different proper motions. These things here have pretty much exactly the same proper motions as the clusters, and so. I'd say that they are probably.
So are there complexes or?
Yeah, they're complexes. I mean, as I said here, these cluster and these cluster have pretty much the same astrometric parameters. This one has slightly different ones, but this is a complex, obviously. And I would expect a lot of things in this area to share the same formation. Does that mean? I mean, initially, I wouldn't think that means that they have to have exactly the same proper motions. But you see things with the same proper motions at some distance, and in fact, you see some small concentrations, which may tell you that apart from the big cluster, I mean, in modern models, you form big clusters by accumulation of the small clusters. So it's possible that some of the small clusters are like behind at some distance.
Another thing was you mentioned at the beginning that there is a relation, statistically proved at some point, between the highest mass star in the cluster and the mass cluster. Can you elaborate a bit more on that, or?
As I said, it's a very long story there.
My work is very interesting.
But this has to do, I mean, you have 2 ways of looking at this. You have a statistical sampling of an IMF, which is completely stochastical. You just pick up. So if you pick 10,000 stars, you have many more chances of picking something that is very unlikely than if you just pick 100. The other one has to do with how you form massive stars, and basically has to do with ideas that you need very strong potentials at the center of the clusters to accumulate a lot of mass and form really massive stars. So if this is the right view, you would expect that the bigger the potential of the cluster, the more likely you are to create very big stars in the center. So that's why I say that you can have a purely statistical interpretation or a more physical interpretation. And there's been a lot of argument between these 2 points of view for the past perhaps 20 years. And I don't think it's been decided so far.
So this is the state of the art.
Yeah.
Okay. Thank you.
No more questions. No question on Zoom, so let's take again.
Thank you.
Yeah.